All right, we're going to begin a chapter on vectors.
And we have studied vectors in the past when we learned about transformations. We did translations horizontally and vertically, and we wrote that in component form. Those were vectors. So we are going to continue to study vectors, so it's going to get a little bit deeper into it. A vector is a quantity represented by an arrow with both direction and magnitude. There's a picture that I have drawn here of a vector. And let's say that this vector starts at the origin and ends at the ordered pair, well, let's say 1 square root of 3. Now, if I were to take this same vector and move it someplace else, like so, that vector has the same magnitude and direction. So let's discuss, I guess, what magnitude means and what direction means. So magnitude simply means, in this context, the length. And let's call this vector v. That is a v with a little segment over top of it. Now, if we meant an actual segment in this class, we draw 2 capital letters with a segment over top of it. This is 1 lowercase letter with a segment over top of it. To denote the length of v, the magnitude, we use this symbol right here, which is like a double absolute value bar. That is magnitude. We will not be doing much with magnitude in this first section. So let's say this down here is vector u. So something that I want to make sure it's clear. If this was a ray, it would have the same symbol. An array starts at one endpoint and goes forever in a direction, never stops. But a vector starts and stops, and let me be more specific, it starts at what is called the tail, and it stops at the tip. It's got a tip and a tail. The tip has the arrow on it, and the tail is where the vector begins. Let's talk about vector components. In component form, vector v, we would use these little absolute, or not absolute value, less than and greater than symbols, which don't mean that in this. So what is the x component? Well, we went to the right 3. We went to the right 1. What is the y component? We went up square root of 3. Now, hopefully you recognize this is a special triangle. Did that intentionally. So if we were asked to find the magnitude of this, I think we also need to have that vector notation on top of that. The magnitude of this is 2. Now, how do I know that? Even though we don't have to know that for this section, this is a special right triangle. Short leg is 1. The long leg is that times the square root of 3. It's going to make the hypotenuse double the short leg, which is going to make it 2. Vector polar form, we're not going to get too deep into this today either, but polar form of this vector, we would put the length of the vector, the magnitude, followed by the angle theta and standard position. Now, we know, once again, that if I take this vector right here, let's just say I draw it off to the side, so I have this right triangle. We know one leg is 1, the other leg square root of 3. Special right triangle, it's got to be when the legs have that relationship, the hypotenuse is 2. This is 30 degrees, this is 60 degrees. So in polar form, this vector would be 2, 60 degrees. 2 is the radius, the hypotenuse, and 60 degrees is the angle in standard position. Once again, we're not going to get into this today. I just wanted to mention it while we're bringing up vectors. We will come back to that someday. Right now, let's focus on what a vector is and how to write it in component form. Let's check out vector addition, graphically using the tip-to-tail method. This is pretty cool. Let's say that we have this vector here. Let's call this vector u. And let's say that we have a vector here. Let's call this vector v. If you were asked to add vector u plus vector v, keep in mind that these vectors, no matter where you put them, it's the same vector. Because vector v has the same length no matter where I move it, and it has the same angle. It's going, let's say, due east. Vector u, no matter where I move it, has the same length, and its direction is some type of a northeasterly type direction. So adding these in the tip-to-tail method, graphically, if I take u, and I put it wherever, it's nice to put it starting at the origin. And then I take v, and I take its tail and put it on the tip of u. Essentially, here's what I'm saying. Starting at the origin, I'm going to travel along vector u, then I'm going to travel along vector v, and I'm going, which essentially means that I am going to start here, and I'm going to end here. So someone else could come along and follow a different path and get to the same ending. That would be this red vector. This is vector u plus v. Now, if we wanted more specifics, if we wanted to know what's the component form of that vector, that's easy. 1, 2, 3, 4, 5. 1, 2, 3, 4. So using the graphical method, we could say that this addition is 5, 4. To the right 5 and up 4. And you can simply use a graph to do that, as we just did. Let's say that we put another vector in here. Let's say that we have a vector that does something like this. We'll call this vector W. Let's say that we wanted to add vector U plus V plus W. Well, if I take this and put her, I'll tell you what, I've got so much in this picture. Let me do this. Let me just put these someplace else. Origin's nice, but I don't want to cloud up my picture. So let's say that we have this. So we start here, we travel along U, and then V, and then we get down here to W. The result of this, also known as the resultant vector, would be this vector here, vector U plus V plus W, which would be going to the right 1, 2, 3, 4, 5, and up 1. Hopefully you'll find that is pretty simple. Vector addition algebraically. Let's take the same vectors, U in component form, went right 2 and up 4. V in component form, it went right 1, 2, 3, and up 0. And W in component form. Now remember, it doesn't matter where these vectors start and stop. It just matters that their magnitude is and their direction. So W goes left to right 0 and goes down 3. So if you were asked to add vector U plus vector V, for example, you would simply take the components, the x components of U and V, and add those together. You would take the components of the y components of U and V and add those together. This would give us a vector with components 5 and 4. Notice, that's the same answer that we got over here when we did it graphically. So if you're asked to do it algebraically or graphically, so this is graphically, this is algebraically, and if you're not told which method to use, do whatever you want. Just a reminder, I couldn't leave this undone here. Here's our little vector dude from Despicable Me. You know what I'm talking about. Vector scalar multiplication. So let's say that we had, let's say that we had a vector that was like this. So we went to the right 1 and up 1. Let's say that was our scale. Like this. And let's call this vector U. What if we wanted to multiply vector U by a scalar 2? Scalar is just a magnitude, it has no direction. That would take this vector, which I'm going to draw right here, and it would double it. Well, I'll tell you what, let me put this up here in the picture. If we double that, instead of going to 1, 1, it would go to 2, 2. So this right here is 2 times vector U. Scalar multiplication is simple. What if we were to take it, and we were to take half of this vector? Tell you what, let me do this. Let me throw another vector up here, vector V. This will make this easier to illustrate. So 2 times vector V might look something like this, twice as big. If we say, what's half of vector V? It might look like this, half the size. Now, it should be noted that if you multiply it by a negative number, that changes this a little bit. If we say we want negative 2 times V, this negative means it goes in the opposite direction. It changes the direction. So opposite direction is what the negative is, and this 2 means you double its length. So it might be a vector that looks like this, comparing that to the original V that we had up here. How would you work this out algebraically? Pretty simple. Let's say that we had vector U, had components 1, 1. If we wanted twice vector U, we would multiply 2 times each of these components, and that would give us, of course, components 2, 2. If we had something like vector V, which goes to the right 2 and up or down 0, if you multiply that by negative 2, we're going to double these numbers and change their signs and get vector negative 4, 0. Let me add one more thing to this, just to make this a little more complicated. So we know what vector U and vector V are from what I have there. Let's just make this as complicated as I can. Let's say if we were supposed to take 4 times vector U and then subtract from that 3 times vector V. How you could show this algebraically, we could take 4 times vector U and then subtract from that 3 times vector V. Subtracting doesn't necessarily make the most sense in most cases. This is usually better written as 4 times vector U plus negative 3 times vector V. So we're going to have vector components 4, 4. And then here, if I change this to addition and then multiply by -3, I get -6 and 0. Then when I add the components, I get -2, 4.